Okay, let's unpack this. When was the last time you really stopped to think about what keeps the world's machines humming along, smoothly? You're not really talking about the big engines or the gears themselves, but those sort of silent heroes that stop them grinding to a halt.
Right.
Lubricants.
Right. They're usually out of sight, out of mind.
Yeah, exactly. Until something goes wrong, and then suddenly they're absolutely critical.
And what's really fascinating, I think, is just how much science goes into something we often just take for granted. So today we're doing a deep dive into the core principles of lubrication. We'll look at how oils and greases actually work, what makes them different, and crucially, why those little additives are so important. The source material we have gives a really comprehensive view.
And for you, listening, this is basically a shortcut to being pretty well informed about a really vital part of almost any mechanical system out there.
Yeah, from everyday things to huge industrial machines.
Right, like your washing machine gears or, massive power turbines. You'll get a much better handle on the functions, the characteristics, the advantages of these fluids and compounds.
And why additives make such a difference, turn simple oil into something high-tech.
So let's start with the basics. The invisible battle that lubricants fight. Friction.
Ah, the enemy of motion.
Pretty much. Think of it as that force, always pushing back, resisting movement when surfaces slide or roll against each other.
And the key thing is you need motion for friction to be a factor. If nothing's moving.
The friction's not really doing anything.
Exactly. And the fundamental goal of lubrication isn't just about reducing friction. It's actually to completely stop metal-on-metal contact.
Completely stop it.
That's the ideal. You want a perfect, unbroken film of lubricant separating those surfaces so they literally never touch. Now, there's different kinds of friction, right? Rolling friction, like in a ball bearing, that's relatively low.
Yeah.
Minimal contact points. But sliding friction, where surfaces are just rubbing constantly, that's much, much higher. That's the real challenge.
And where lubrication is absolutely essential.
Paramount.
So what are the things that influence how much friction you actually get? What makes it better or worse?
Okay, there are about 5 main factors to consider. First is surface finish, even stuff that feels perfectly smooth.
Like a polished table.
Yeah, exactly. Under a microscope, it's actually full of tiny little peaks and valleys. We call them disparities.
Disparities.
Right. So when you get new equipment, the surfaces are microscopically rougher. This is why we talk about a break-in period.
Okay, so friction is higher at the start.
Initially, yes. As the machine runs, those tiny bumps, the disparities, they wear down. The surfaces get smoother and friction naturally drops.
That makes sense. Like breaking in new shoes, they get more comfortable. But does that initial wear cause problems, like extra bits floating around?
That's a really good point. Yes, there's some initial wear debris, which isn't ideal, but overall the process helps optimize the surfaces for contact later. Managing that initial debris with the right lubricant is key, though, to avoid early damage. Second factor, load. Basically, how much pressure is pushing the surfaces together.
More pressure, more friction.
Exactly. More load means those surfaces get squeezed harder, friction goes way up. Third is speed, how fast the surfaces are moving relative to each other.
Faster means more heat.
Generally, yes. High speeds mean more kinetic energy, which turns into heat, and heat is a direct byproduct of friction.
Go.
Fourth, the lubricant itself, or maybe more importantly, the lack of it.
Right. No lube means...
It means metal on metal, which means extreme friction, loads of heat, and eventually, bang, machine failure, catastrophic.
Okay, and the last one.
Temperature.
Yeah.
Temperature affects the surfaces themselves, but critically, it affects the lubricant's viscosity.
Viscosity, how easily it flows.
Precisely. How thick or thin it is.
That brings us to the idea of the fluid film itself. You mentioned wanting a film, but the thickness of that film actually matters quite a bit, doesn't it? It defines the type of lubrication happening.
Exactly right. It's not just lubricated or not, it's more like a spectrum.
A spectrum. Okay.
At one end, you have what's called boundary lubrication. This is where there's hardly any fluid between the surfaces. They're mostly touching, maybe with just a very thin layer clinging on.
So high friction here.
Very high friction, lots of wear. It's the least effective state. But then as you maybe increase the speed or use a thicker lubricant or even reduce the load, the surfaces start to lift apart. That fluid film starts to actually form.
And I guess friction drops dramatically then.
Absolutely. That's when you enter mixed film lubrication. Here, the surfaces are partly separated by the film, but still partly touching. And you see this sharp drop in the friction coefficient as the fluid starts carrying more of the load. Less rubbing.
Okay, so mixed is better than boundary. What's next?
As the film builds up even more, you get into elastohydrodynamic lubrication, EHD for short.
Elastohydrodynamic. That's a mouthful.
It is. Think of it like this. Imagine two smooth, slightly flexible surfaces, maybe like hard rubber, being pressed together. Right where they almost touch, the oil film gets squeezed incredibly thin. So thin that the pressure actually deforms the surfaces just slightly.
Like a tiny cushion.
Exactly. Just enough deformation to maintain that microscopic separation. It's a really fine balance.
Wow.
And then the ideal state, the goal we're usually aiming for, is hydrodynamic lubrication, or full film.
Full film. Sounds good.
It is. Here, the two surfaces are completely, totally separated by a continuous, relatively thick fluid film. Metal never touches metal.
Lowest friction, longest life for the parts.
That's the aim.
Okay, that's fascinating, just thinking about the film. So with that ideal in mind, let's talk about oil specifically. What are the key things you look at when you're evaluating an oil's characteristics?
Well, the number one most fundamental property is viscosity. We mentioned it before. It's the liquid's resistance to flow.
Honey versus water.
Perfect example. Honey is high viscosity. Water is low. The higher the viscosity, the harder it flows. Now, how we measure it. Traditionally, it was Sable Universal Seconds, or SUS.
How did that work?
You basically timed how long it took for a specific amount of oil to flow through a standard opening, a Sable flask, at a set temperature. It's a bit old school now.
So what's used today mostly?
Today, we mainly use the ISO 3448 system. That's the International Standards Organization standard. It uses units called centistokes, measures flow through very fine capillary tubes, and uses Celsius for temperature.
More precise, I guess.
Yes, and it's the global standard. The good thing is you can always find conversion charts. You can convert ISO VG grades to SUS, or even to the SAE grades you see on car engine oil, like 10W30.
Ah, right. I always wonder what those numbers meant.
And a really crucial point about viscosity for almost any lubricant. As temperature goes up, viscosity goes down.
So hotter oil gets thinner.
Exactly. It flows more easily.
Okay, so viscosity changes with heat. But then there's something called viscosity index, or we were at 6. What does that tell us? Why is it important?
Size is super important for real-world use. Viscosity index measures how much the viscosity changes with temperature.
So less change is better.
Generally, yes. A higher psi number means the oil's viscosity changes less when it gets hot or cold. That's really desirable.
Why is that so good?
Think about your car engine. It needs to start on a freezing morning, but also run efficiently on a hot highway. A high C oil can handle that range. Its viscosity stays more stable across those temperature swings. Without a high 6, you might need different oils for summer and winter.
Right, that would be a pain. Okay, what else defines an oil?
Another key one is pour point. This is simply the lowest temperature at which the oil will still flow. Pour.
So critical for cold places.
Absolutely. If you're operating machinery in, say, Alaska in winter, you need an oil with a very low pour point. If it gets too cold and thickens up so much, it won't pour.
It can't circulate.
Exactly. It won't get to the parts that need lubricating. Instant problems.
Makes sense. And then there's safety terms. Flash point, fire point. What's the difference?
Crucial for safety, especially anywhere there's heat. Flash point is the temperature where the oil gives off enough vapor to ignite briefly if there's a flame source. Just a quick flash, then it goes out.
Okay, just a flash.
Right. Fire point is higher than the flash point. At this temperature, the oil gives off enough vapor to ignite and keep burning. It sustains a continuous flame.
Ah, okay. So you definitely need to know those, especially if things get hot.
Vital. You don't want the lubricant itself becoming a fire hazard.
So these petroleum oils, they come from crude oil, right? Does the type of crude oil matter much for these properties?
Oh, absolutely. The base stock, the raw crude oil, makes a difference. There are 3 main types. You've got paraffinic-based crude. Generally gives you a higher viscosity index, which is good, but also a higher pour point, not so good for cold.
Okay.
Then there's naphthenic base, typically lower VI, but also a lower pour point, better for cold. And importantly, it's less likely to form hard carbon deposits when it gets really hot.
That sounds useful.
And the third is asphaltic base, which is sort of similar in characteristics to naphthenic. Each base stock has pros and cons depending on what you need the final oil to do.
Wow, okay. So we've got these base oils with inherent properties, but you mentioned earlier that plain oil often isn't enough on its own. That's where additives come in.
Exactly. The additives are like the special forces. They turn a basic base oil into a highly engineered fluid that can handle specific, tough jobs.
So what kind of jobs do these additives do?
Well, first up, you have viscosity modifiers. These are complex molecules, polymers, that are added to help the oil resist thinning out too much at high temperatures.
So they boost the ZI we talked about.
Essentially, yes. They expand the oil's useful temperature range, keeping that protective film intact even when things get hot. They stop it getting too runny.
Got it. Keep it from getting watery. What else?
Then you have detergents. Think of them like tiny cleaners. They prevent soot, sludge, and other contaminants from sticking to surfaces. They also neutralize acids formed during combustion or oxidation.
So they keep the engine parts clean, prevent buildup.
Exactly. Help prevent varnish and carbon deposits. You find detergents in almost all modern lubricants. Closely related are dispersants.
Detergents and dispersants. What's the difference?
Good question. While detergents clean surfaces, dispersants work on the contaminants floating in the oil. They keep tiny particles, dirt, metalware, soot from clumping together into bigger lumps that could clog things up.
So detergents clean the walls, dispersants keep the stuff in the middle from sticking together.
That's a great way to put it. They keep everything finely suspended. Then you have anti-wear agents and extreme pressure EP agents.
Those sound important.
They are, especially when the load is really high. Under intense pressure, the regular oil film can get squeezed out. These additives form a protective chemical layer right on the metal surfaces, preventing direct metal-to-metal contact and reducing wear or even seizure.
So they kick in when the going gets really tough.
Precisely. Then there are antioxidants. Remember, oil is organic, it reacts with oxygen, especially when hot. Oxidation breaks down the oil, makes it thick, sludgy, less effective.
So antioxidants slow that down.
Exactly. They significantly extend the oil's useful life by inhibiting that chemical breakdown.
And what about rust, water getting in?
That's where rust and corrosion inhibitors come in. They help the oil cling better to metal surfaces, forming a barrier that keeps out oxygen and moisture, the things that cause rust and corrosion.
Okay, one more.
Yes, anti-foam additives, sometimes called foam inhibitors. Oil can sometimes trap air bubbles and turn into foam, especially if it's churned up a lot.
And foam doesn't lubricate well.
Not at all. Think about washing your hands with just soap suds versus the actual liquid soap.
Right, the suds don't really clean much.
Same idea. Foam is mostly air. It can't provide a proper lubricating film. So these additives prevent foam from forming or help it break down quickly.
I know exactly what you mean. I tried cleaning a greasy part once with just the foam from a degreaser. Useless. Felt like I was just pushing bubbles. Okay, so that's oils and their additives. Let's shift gears, literally, to grease.
Okay.
You mentioned earlier, grease is only about 10% of global lubricant use. If oil seems so versatile with all these additives, why use grease? What makes it the right choice sometimes?
That's a really insightful question. Even though oil is used more overall, grease has 4 distinct advantages that make it absolutely essential for certain jobs.
Okay, what are they?
First, sealed bearings. Grease can be packed into bearings at the factory, and then the bearing is sealed. The grease stays in, contaminants stay out, often for the life of the bearing.
Oh, like lubricated for life parts.
Yeah, exactly. Second, grease stays put. It's thick, it doesn't just run out like oil would. This makes it perfect for places where you can't easily supply a continuous flow of oil or where gravity would just pull oil away. Think open gears or vertical shafts.
Makes sense, it clings.
Third, generally speaking, grease can handle higher temperatures than many conventional oils, especially in localized hotspots. And fourth, and this is a big one for maintenance.
The rest work.
Exactly. Grease usually decreases the frequency of lubrication. Because it stays put and can handle conditions well, you don't need to reapply it nearly as often as you'd need to change or top up oil in many applications.
Right. Like car wheel bearings versus engine oil.
Perfect example. Wheel bearings are packed with grease and might go 50,000 miles or more. Engine oil, you're changing that every few thousand miles, different jobs, but it shows how grease can really extend those service intervals.
So if it's not just thick oil, what is grease made of?
Good question. It's mostly oil. About 80 to 90% is typically a petroleum base oil, similar to lubricating oils. But that oil is held in suspension by a thickening agent, usually called a soap.
Soap? Like washing soap?
Huh? Not quite the same. It's a metallic soap, chemically speaking. And then, just like oils, you add additives to improve performance, anti-wear, rust inhibitors, etc. The type of soap thickener used is what really defines the grease's properties and where you'd use it.
Okay, so different soaps make different greases.
Exactly. Let's run through the main types. First, calcium soap grease, sometimes called lime soap. It's cheap. It actually contains a little water, maybe 1 to 3%, which helps bind the soap and oil.
Interesting. Water in grease.
Yeah. It limits its temperature range, though usually below 180 Fahrenheit or so.
Yep.
Good for low speeds, and importantly, it resists being washed out by water, so it works well in wet environments.
Okay, calcium for wet. What's next?
Sodium soap grease. Also fairly low cost, kind of a general purpose grease. It can handle higher temps, maybe up to 250 Fahrenheit. It often has a kind of fibrous, stringy texture, used in some bearings. But here's the big catch. It's water soluble. It absorbs water.
Water soluble, so absolutely not for wet places.
Definitely not. This is critical. You would never want to use sodium soap grease on, say, boat trailer wheel bearings.
Ah, because launching the boat.
Exactly. The water would wash the grease right out or emulsify it. Then you get metal on metal contact, overheating, bearings could seize up, the wheel could literally come off the trailer, catastrophic failure potential. So sodium soap, dry environments only.
Wow. That's a vital distinction. Okay, what else?
The most common general purpose type is probably lithium soap grease, often just called multi-purpose grease.
I've seen that label.
Yeah.
Yeah.
It's good stuff. Handles higher temps, maybe up to 300 Fahrenheit. With the right additives, it works well in the cold too, and it has good water resistance. Much better than sodium soap.
So more versatile.
Very much so. Think about lubricating the suspension points on a snowmobile chassis. It's cold, it's wet. Lithium grease handles those conditions well, preventing wear and rust.
Good example. Are there others?
Yes, there are complex soap greases. These use more sophisticated metallic thickeners, not just simple soaps. They're primarily designed for very high-temperature applications, where other greases might break down or melt.
They specialize for heat.
Right. They tend to be more expensive, and sometimes they don't respond quite as well to additives as lithium grease does. And finally, you have synthetic greases.
Like synthetic oils. Better performance, higher cost.
Generally, yes. They use synthetic base oils instead of petroleum. Superior performance, great heat resistance, they don't oxidize easily, very efficient. But yeah, they cost more. There are different types, like organic esters for wide temperature ranges, polyglycols for high temps but maybe less water resistance, silicones, which are pricey but handle high heat and water well, and synthetic hydrocarbons. Each is tailored for pretty specific, demanding applications.
What an incredible range. From basic calcium soap to high-tech synthetics, it really drives home how lubrication isn't just one thing. It's a whole field of tailored solutions. So we've gone from friction basics through oil properties, additives, the different lubrication regimes, and now grease types. Phew. It's clear this is way more complex and way more important than most people probably think. Truly the unsung hero.
Couldn't agree more.
So, after covering all that ground, if you had to boil it down to one single most important piece of advice for anyone dealing with lubricants, maintaining their car, operating machinery, anything, what would that golden rule be?
That's easy, and it's absolutely critical. Always, always follow the manufacturer's recommendations and specifications.
Stick to the manual.
Yes. Every machine, every apparatus is designed by engineers to work under specific conditions using lubricants with specific properties, viscosity, additives, base type, everything. Using the wrong stuff
Leads to trouble.
It can lead to inefficiency, accelerated wear, overheating, and potentially catastrophic failure. Unless the manufacturer issues an official update or bulletin recommending a change, stick rigorously to what they specified. That's the safest, most reliable path. Don't second-guess the engineers who designed it.
That's a really powerful practical takeaway. Follow the specs. Even with all this knowledge we've discussed, the ultimate guide is often right there in the documentation.
Precisely.
It kind of leaves you thinking, doesn't it? In a world where machines are just getting more complex, more specialized, how could understanding these lubrication fundamentals actually empower us? Not just to follow the rules, but maybe to optimize things better. Like, could understanding why a certain lubricant is specified allow someone to maybe question outdated maintenance routines or suggest improvements based on actual operating conditions using informed insights rather than just habit?
That's a fascinating thought. Moving beyond just operation to true optimization, perhaps? Using this knowledge proactively? Definitely something to consider.
Well, thank you for joining us on this really quite slippery deep dive. Hopefully you found it useful. Keep asking questions, keep learning, and keep that curiosity running smoothly. We'll see you next time.